This is something, frankly speaking, I cannot understand or interpret. How can this be? And that's why I claim that this is one of the most amazing observations ever made. But it is a fact of nature. It is a fact of life, if you like. The speed of light is the same in both directions. Why it is so, I really do not know. Now the implications of this result were in fact best explored by a young scientist from Bern, Switzerland, who was around 26 years old at that time. And in fact, he had the courage to put the results of the Michelson-Morley experiment before the long known and well accepted ideas of the Newtonian mechanics. So in fact, Einstein proposed to replace the old Newtonian mechanics with the Galilean relativity, etc., with a new science, which is called today the theory of the relativity. And the theory of the relativity is based on two postulates, which are extremely simple. And the first postulate is that the laws of the nature are the same in all inertial frames of reference. The inertial frame is a frame that is moving at a constant speed. And the speed of light in the vacuum is the same in all inertial frames of reference, which is the observation and result of Michelson-Morley. So these two postulates look very similar. But there is an amazing amount of information, very interesting information, that can be derived by using, in fact, rather simple mathematics from these two postulates. They contain incredible consequences, like time dilation or length contraction. From these postulates, one can show that, in fact, time intervals, the space separation between objects, and simultaneity are not absolute. That space and time are related to the observer, and the measurement of time depends on the measurement of the space and vice versa. And more importantly, in the theory of the relativity, we cannot think of space and time as independent quantities, as separate entities. They are somehow, they must be somehow combined in a single entity, which is today called the space and time. So space and time in relativity are somehow fused together, somehow united, to form what is called today the four-dimensional space-time continuum. Now this idea of the four-dimensional space-time was not introduced by Einstein, as many people wrongly claim today. It was introduced by his professor of mathematics called Hermann Minkowski. Minkowski was Einstein's professor, and he has a very bad views about Einstein. He called him a lazy dog, and he was extremely unhappy with his students and with his student, and in fact, the history tells us that Minkowski decided to do some work in relativity. He was a pure mathematician, not interested by physics, because he had read Einstein's papers. So he decided to do something better than his former lazy student. And possibly he succeeded. So the idea of the four-dimensional space-time is today the basis of the theory of the relativity. Now, the special relativity is a very fascinating topic, but there is an even more interesting field, and this is the field of general relativity. After 1909, Einstein started to think how to include acceleration in special relativity, and in fact we introduced the so-called non-inertial frames. And this, in fact, this study of how to include acceleration in relativity, in fact, turned out to be a theory of the gravitation. So starting from the study of acceleration, Einstein derived a theory of the gravitational field. And this extended theory of the relativity, which was finished by Einstein around 1916, is called today the general theory of the relativity. The general theory of the relativity is also based on two basic principles. And the first principle is called the equivalence principle. It was described very well by Einstein in some thought experiments about some lifts. These are the famous Einstein lift experiments. And the basic idea, in fact, of these experiments is that we cannot distinguish gravitation from acceleration. So if we are in a lift which is completely isolated from the stars from outside, and this lift has some kind of engine which accelerates the lift upward by an acceleration g, it is impossible to tell if this is an acceleration due to gravitation or due to the engines of the lift. So the lift can have some engines pushing down at acceleration g. So the effect is exactly the same as here it would be a massive object. So we cannot distinguish gravitation from acceleration. And the same holds true if the lift is falling free in the gravitational field. By accelerating the lift, we can cancel the gravitational force. So from these experiments, in fact, and this is the first postulate of Einstein, is that in fact we cannot distinguish gravitation from acceleration. So this is called the principle of equivalence, and it states that inertial and free-falling systems are equivalent. So by appropriately choosing a non-inertial frame, giving him an appropriate acceleration, we can either cancel, either destroy the gravitational field, or we can create a gravitational field. The second principle is even more interesting. And in fact, it is also based on this analogy. Let's assume that we have a rubber sheet. And at the center of this rubber sheet, we place a heavy object. As a result of this, in fact, the sheet is deformed. The initial flat geometry of the sheet will become very complicated. Now, if we launch some particles in this, on this sheet, we observe that in fact they will move on some parabolic or elliptical orbits, not because there is some force acting on these particles, but simply because the sheet is deformed due to the presence of the heavy mass. So from here, Einstein in fact assumed that gravitation is just a manifestation of the space-time geometry. So where there is a mass, around the mass, the space-time is somehow curved. It is deformed like in this example. And in fact the particles are moving freely around the central object, not because they are attracted by some force, but because they are forced to this kind of motion by the geometry of the space-time. This is Einstein's second postulate, that gravitation is a manifestation of the geometry of the space-time. So based on these ideas, Einstein proposed his very famous equations of general relativity, in which the basic idea is that the curvature of the space-time is proportional to the matter. So more matter we have, more the space-time is curved. And the physical interpretation is that if a curvature is equivalent to gravity. Now generally by matter we mean all forms of energy, including pressure. In general relativity also pressure is a form of energy, and it has it has some mass. And